Hi Year 7. Today's lesson we're going to be focusing on square roots and cube roots, but we're going to be using prime factorisation. So you're going to be doing a little bit more of your prime factor trees, which will give you some more practice. We'll be looking at the part in blue below, so that little 3 and the tick means cube root of 8 and much bigger and trickier numbers like 6,859 and 4 times 4. First of all, we're going to start off by looking at your exit ticket, so please have that to hand to mark. There'll be approximate timings on Show My Homework, and any questions, any issues, just message me. Okay, well done everybody that submitted this. I can see a whole mixture of responses. Some of you have really got to grips with the alternate method. Some of you have done listing, which I didn't want you to do for this question. So if you're somebody that's still doing listing method for lowest common multiple, please can you try and work hard on the alternate method or Venn diagram method. So first of all, I'm going to show you alternate method and the answers. So I just want you to mark those. So remember, we start with a table and we're going to break down 105 and 225. Okay, so I'm going to look at 105 and 225 and I'm going to find a number that divides into both of them that is the same number, and I'm going to pick 5 because both numbers end in 5. So I'm just going to divide 105 by 5 and I get 21, and then I'm going to divide 225 by 5. Okay, so this is where it gets tricky, and some of you got this far and we concluded the highest common factor was 5, but actually 21 and 45 have some other numbers in common, so we can actually divide those further. So good test, if the numbers are both even, then you can always divide by 2. If the digits of the numbers add up to a multiple of 3, then they're in the 3 times table. So in 21, 2 plus 1 is 3, that means 21 divides by 3. If you add 4 to 5, 4 plus 5 is 9, 9 is in the 3 times table, that means 3 is a factor of both, so 3 is the next number I'm going to pick to divide into 21 and 45 now. Okay, so I end up with 21 divided by 3 is 7. 45 divided by 3 is 15. Now 7 is a prime number and 15 is not, but what that means is, on our bottom row, the only number in common between 7 and 15 now is 1, which means we don't go any further with our table. Okay, so our highest common factor is going to be this bit here multiplied together. So whichever method you did, if you got highest common factor of 15, then that was correct. Now our lowest common multiple is going to be all of this bit circled in green multiplied together. Okay, you may have needed to use a calculator for that, that's absolutely fine. So you should have got 1,575 as the lowest common multiple. Now I know 1 or 2 of you did the Venn diagram method, which is great, so what I'm going to do on the right hand side here is just draw what that should have looked like. So long as you ended up with the highest common factor of 15, lowest common multiple of 1,575 at the end. I don't mind which method you use one that you are most comfortable with. Okay, so just an example there. Remember, to find the highest common factor in our Venn diagrams, we multiply together just the numbers where our Venn diagrams overlap, so 3 times 5. Our lowest common multiple, we multiply all the numbers in our Venn diagram. So I'm not going to read these to you, but I just want you to read through these definitions and copy them into your book or onto your paper so that you've got a record of these as we go through the lesson. Okay, so just have a go at these questions. Remember, if we say what is the sixth square number, we're talking about 6 times 6 and the result of that. Okay, so just see if you can work out what these are without using a calculator. Pause the video now. Okay, and just mark your answers. Hopefully you got these. Remember, the first square number, first cube number is going to be 1, and the cube root of 1 and the square root of 1 is also 1, so that's a special case. First of all, we need to define what a perfect square is. So we have a square number such as 9, and if we break this down into a product of its primes, we can write it as 3 times 3. So we can say because we have a pair of prime factors, 9 equals 3 times 3, that pair of prime factors means that it is a perfect square. We're not going to end up with an awkward number. Okay, so we will look at numbers where there might be more than one pair of prime factors, or there might be a pair of prime factors and another number. First of all, what I would like you to do is, using your prime factorisation, so drawing your factor trees, find the square root of these numbers here, and just pause the video and I'll go through the answers in just a moment. Okay, so hopefully you've worked through those. Your answers will be coming up shortly. Okay, so just pause the video to mark your answers there. So what you'll notice is, for the numbers, all of these are examples of square numbers, and all of them have pairs of prime factors, so that's really important. So you'll see I've underlined the different pairs in different colours. Hopefully you should be able to see those. Because there are pairs of numbers, each prime factor number is paired with itself, we can say that these are square numbers. So we're going to do an example, and then you're going to have a go yourself. So first of all, it says, using prime factorisation, we want to find the square root of 225. So our first step, just as it has been with all of the exercises we've been doing recently, is to break 225 down into a factor tree, and we'll end up with a product of primes at the end. So we can break 225 down into 5 times 45. 5 is a prime factor, so we'll circle it, and then we'll break 45 down further because it's not a prime number. So 5 times 9 is 45, 5 is a prime number, 9 is not, so we need to break that down again. And finally we end up with 3 times 3 at the bottom to create 9, and then we'll write that as a product of its primes. So it will look like this as a product of primes. 225 equals 3 times 3 times 5 times 5. Now, thinking back to the last question, we have 2 pairs of prime factors in our product of primes, and that means this is going to be a perfect square, which is what we want. So our next line in blue here, we can say the square root of 225 equals the square root of its product of primes. So to find the square root of 225, what we're going to do is take one number from each of those pairs and multiply them together. And it's going to look like this. Okay, so we've got 3 times 3, so we're going to take one of those, and 5 times 5, we're going to take one of those, and therefore we can say the square root of 225 is 15. Okay, so we've done a prime factor tree, we've written our number as product of primes, we've seen that it contains pairs of the same numbers multiplied by themselves, and only pairs of those numbers, and then we've taken one of each of those numbers, times them together to get our square root. Right, it's going to be your turn now, so I would like you to have a go at finding the square root of 256, copying the method we've just done. Pause the video now. Okay, and I'm just going to show you the answer now. So first of all, we're going to draw our prime factor tree, breaking 256 down into a product of its primes. Okay, and your prime factor tree may look like this. You might have broken it down in a different way, but at the end of it, you should have got 256 equals 2 times 2 times 2 times 2 times 2 times 2 times 2, or you might have had 2 to the power of 8. But I would leave it actually split up into this separate product of primes, so you can see if there are pairs of numbers. If we look at that, we've got an even number of 2's, which means we've got 4 pairs there, which is really important. It means that we are going to get a perfect square from it. So we can say the square root of 256 equals the square root of 2 times itself 8 times. And then what we're going to do is we're going to take one of the 2's from each pair, and then we are going to multiply them together to find out what our square root is. And so you should have got an answer that the square root of 256 is 16. Okay, in the last example, we had an example where we had a perfect square and therefore we can find the square root of it where we've got a whole number or an integer. In this example, we're not going to have that, and I just want you to see this too. So we're going to break this down into product of primes and then look at what we've got. Okay, and if you do that, you'll end up with this factor tree here. You may have broken it down differently. That doesn't matter. You will still end up at the end of it with 240 equals 2 times 2 times 2 times 2 times 5 times 3. Okay, so let's have a look at what we've got. How many pairs of the same number do we have? So we've got one set of 2's, and we've got another pair of 2's. But then we've got this 5 and we've got this 3 that are on their own. So what that means is this is not going to give us a perfect square. We can still write 200 square root of 240 is the square root of 2 times 2 times 2 times 2 times 5 times 3. But when we come to this second stage here where we want to write this, we can't actually do anything with this bit. It's problematic. So instead we're going to say it's not a perfect square, and the questions that you'll see will just be asking you to say why it's not a perfect square. So just comment on the fact that there are not pairs of prime factors only, there are other prime numbers as well. Okay, so you're going to have a little go at this question on the right now, so you're going to go through the same process and just comment like I have at the end. Pause the video now. Okay, and I'm just going to put the answers up now for you to mark. So your answer might look something like this. Note, when 288 is broken down to its prime factors, there's a 2 that is not paired with another 2, therefore this is not going to be a perfect square, and the root will not be a whole number, so then you won't worry about working out what the square root of that is in that case for this lesson. Okay, so just have a go at these questions. There are some more questions on the next slide too, following the method we've just gone through. Okay, and this is the second set of questions. Pause the video as needed. Okay, and answers are here. Pause the video so you can mark them. Okay, so the step up from finding the square roots is finding the cube roots, and we follow an identical process to begin with. So I'm just going to break 64 down into a product of its primes to start off with. Okay, so once we've done that, we'll end up with 64 equals 2 times 2 times 2 times 2 times 2 times 2. Okay, we want to find a cube root. So remember, our definition of a cube root is a number multiplied by itself 3 times, and we want to find that. So this time what we're looking for in our prime factorizations are triplets, or sets of 3 numbers that are the same, and only that. So we've got a set of 3 here, and we've got a set of 3 here. So we can say that the cube root of 64 is equal to 2 times 2 times 2 times 2 times 2, and then I'll show you the next bit. So the next bit, what we're going to do is say this. Apologies, that should be cube root there. So the cube root of 64 is going to be one number from this triplet multiplied by one number from this triplet. So we can say the cube root of 64 is equal to 2 times 2, which is 4. And you can check that. If you do 4 times 4 times 4, you will end up with an answer of 64, so we know that that's the right answer. Now, have a go at the question on the right and just pause the video now. Okay, and I'm going to show you the answer to this now. Remember, we're looking for triplets of prime factors, and that only in this particular case. So this one's actually a little bit simpler than the example on the left. We end up with 125 equals 5 times 5 times 5, and then we can say the cube root of 125 equals the cube root of 5 times 5 times 5. We've only got one triplet here, so we're just going to take one of those, which is 5, and that means our answer, our cube root of 125 is 5. You may know that anyway, but I would hope that you still had a go at this example. Okay, and this is going to be an example of where it's not going to end up being a nice cube number at the end, and we're going to look at why. So let's start by breaking this down into product of its primes. Okay, so once we do that, we should end up with this. So this is another reason why it's really important that you're writing your prime numbers in order of smallest to biggest, because it makes it so much easier to see your triplets here, okay? So we're looking for triplet numbers. We've got this, 2 times 2 times 2, but then we've got this on its own and this on its own, which means when we write the cube root of 80, although we can say it's 2 times 2 times 2 times 2 times 5, there's only one pair of one triplet in here, and then we've got these two numbers on their own. Therefore, we can say it's not going to be a perfect cube number, and we wouldn't take this any further for the sake of today's lesson. Okay, so I would like you to have a go at this question on the right. So, following the same process, find the cube root of 150 using prime factorisation. Pause the video now. Okay, and I'm going to show you the answer now. Okay, so similar to the one on the left, if we break this down into product of its primes, there aren't any triplets in here. They've got this number on its own, this number on its own. We've got a pair of numbers here, but no triplets. Therefore, we can conclude this is not a perfect cube. And the reason is because it has no triplets in that composition, and it doesn't comprise only of triplet product of primes. Okay. I would like you to have a practice now with these. So remember, integer means whole number. So we want to know if they have cube roots. So what you're doing is checking whether that product of primes comprises only of triplets. The next question 7 is not a spelling mistake. Read the instructions quite carefully and just have a go at this. Pause the video and then check your answers when you're done. Okay, and answers are up here. Okay, finally there is an extension if you finished everything and you want some more to do. So what we have here is a grid on the left. Don't worry about the grey boxes. The grey boxes will have no numbers written in them. But for example, 24 up here, what you're looking to do is break this down into product of primes. So you're going to have exactly 4 factors when you break it down into product of its primes. Bearing in mind this is nothing to do with what we're just doing apart from the factor trees, and what you're going to do is put those numbers around the boxes, so like this, but not necessarily here, and then they need to meet up with the prime factors of this number. So you're going to probably write in pencil and just see if you can work out this puzzle. It's quite tricky, it's going to need a bit of resilience. Have a go. Okay, and the answers are up here.